All right, so cyclohexane, this is going to be the star of the show. In that earlier diagram, we saw it had no strain in it, so it has no angle nor any torsional strain. So it's essentially all strain-free. Obviously means that it's not flat because then the bond angles wouldn't be 109.5 degrees. And in our case, it's very commonly found in nature. You'll see cyclohexanes in all kinds of biomolecules. And so this really makes it the star of the show, right? We're going to spend most of our time with these cycloalkanes studying cyclohexane. And so here's our flat skeletal structure. Obviously, it doesn't look like this in real life. What's going to happen is one of these carbons is going to go into the back of the board. The other carbon is going to go out into the front of the board or out of the board. And then these four are going to stay in the same plane. And so this isn't going to be a Newman projection, but if you were just to look at it, right, what you would see here is four carbons essentially in the same plane, right? So these are my carbons in blue. I didn't draw them exactly in the same plane, but they would be in the same plane. And then they're attached to one carbon that's coming out of the board and one carbon that's going back into the board. So this is the conformer with the least amount of strain or zero strain, and this is called a chair conformer. The reason it's called a chair conformer is because if you think about it, it looks like a chair, right? So if you sat down there, there's your little cyclohexane chair.